In this lesson, we're going to look at graphs of exponential functions and logarithmic functions and transformations of those graphs. So let's get started. If we wanted to sketch the graph of the exponential function f of x equals 2 to the x, the domain of this function is all real numbers. There isn't any x value that we can put into this function that is going to give us an undefined answer. So all x values are going to work for us. So the domain is this set of all real numbers, negative infinity to positive infinity. If we put x equals 0, you can see that we'll get 2 to the 0, which is 1. So this function is going to have one y-intercept, and that is at the point 0, 1. This function will not have any x-intercepts, because if you'll look at the function, there isn't any x value that we can put into this function that'll give us an output of 0. So there are no x-intercepts, no zeros, no roots to this parent function 2 to the x. So let's look at some inputs and outputs for this function. We've already talked about this one. If we put in 0, we're going to get 1. If x is 1, that's 2 to the 1, that's 2. If x is 2, that's 2 squared, that's 4. So we can see as x gets larger and larger and larger, 2 to the x is going to get really, really, really large, really, really, really fast. And we know that about exponential functions. If we put negative values in here, for instance, 2 to the negative 1 is 1 over 2 to the positive 1. 2 to the negative 2 is 1 over 2 squared. 2 to the negative 3 is 1 over 2 cubed. So as x gets large in the negative direction, the outputs of this function get really, really, really small. They tend towards 0, but they never equal 0. So this function will have a horizontal asymptote that is the x-axis, or the horizontal line, y equals 0. The range of this function is all positive values greater than 0 all the way up to positive infinity. So here's what the graph looks like, and we can tell just from the table of values, just as we said, if we put 0 into this function, we're going to get 1. As x gets larger and larger and larger in the positive direction, the outputs get larger and larger and larger. As x is negative, those negative input values make the outputs stay positive but get very, 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 very small. So we're not surprised by what the graph looks like. So this is what the parent function of f of x equals 2 to the x would look like. It is a increasing function. It increases everywhere over its entire domain, has a horizontal asymptote that is the x-axis, which is the horizontal line y equals 0, has one y-intercept, which is the point 0, 1. So lots of stuff that we can determine about this parent function. And in a little bit, we'll talk about what transformations of this function might look like. So the domain is all real numbers for this function as well. Now we have a base that's 1/2 instead of 2. And we have a variable exponent, what makes it an exponential function. Again, no x value can be put in here that we won't have a well-defined output, so no problems with the domain, all real numbers. If we put 0 in, we get 1/2 to the 0, which is 1. Same y-intercept is 2 to the x. Again, no x-intercept. There isn't an x value we can put into this function machine that will give us an output of 0. So much like 2 to the x, 1/2 to the x is going to behave the same way for those kinds of ideas. The difference is how it behaves in the plane as far as increasing, decreasing. So we know we have this y-intercept value here. If x is 1, then y is 1/2. If x is 2, y is 1 over 2 squared. If x is 3, it's 1 over 2 cubed. So we can see as we put larger and larger and larger x input values in, we get smaller and smaller and smaller, but still positive output values. So this is a decreasing function for this half of the real number set. If we put negative numbers in for x, we get 1/2 to the negative 1. So that's 1 over 2 to the negative 1. We cross the line, change the sign, and we'll get positive 2. 1/2 to the negative 2 is 1 over 2 to the negative 2. We cross the fraction line and we get 2 to the positive 2, or 4. So as we put bigger and bigger and bigger negative values into this function, we get bigger and bigger and bigger positive outputs. So this function increases as we go to the left, but decreases without bound when we look like we normally do, which is from left to right. So it approaches 0, has the horizontal asymptote of y equals 0, and has the same range as f of x equals 2 to the x. So this function in essence just looks like the graph of f of x equals 2 to the x having been spun around or reflected over the y-axis. So this is what all functions, all exponential functions that have a base between 0 and 1 are going to be strictly decreasing functions. They all go through the point 0, 1, and all functions that have a base greater than 1 will look like the graph of f of x equals 2 to the x. They will look like the graph of this function. They're strictly increasing. They all have a horizontal asymptote that is the x-axis, and without any transformations or translations, they all contain the point 0, 1. So that's true for all exponential functions. So here are both graphs on the same xy axis. They are symmetric about the y-axis. They are reflections of one another. Again, the difference is the value of the base. We know we can't have a negative base, we can't have a base that's 0, and we can't have a base that's 1. So of all the other real numbers, the bases in between 1 and 0, their graphs are going to tend to look like this. For bases greater than 1, their graphs are going to look like this before any translations are done on them. So in general, for all exponential functions for positive bases not equal to 1, they all have a domain that is all real numbers. Before any translations or transformations, they all have a range that is positive values, 0 to positive infinity. They all pass through the point 0, 1. They all have that same y-intercept. They are continuous over their domain, and if the base is greater than 1, they are strictly increasing over their domain, and if the base is between 0 and 1, they are decreasing, strictly decreasing over the entire domain. So let's look at transformations. We know we've talked about transformations already and done some review. We know that if we have a negative in front of our function, it means one thing. If we have a negative inside our function, it means another thing. If we have a value added or subtracted inside with x, that means something. If we have a value added or subtracted outside of the whole function, that means another transformation. And it turns out that the transformations that we already know are still true. If we add or subtract a whole number outside of our function, that is a vertical translation. So this function would just be the parent function 3 to the x translated 4 units down in the plane. Here is a x plus 1 or a minus negative 1 inside the function. So we know that's going to be a horizontal translation, and that's 1 unit to the left, just like what we're used to. Here's a negative in front of our function, and that is a reflection over the x-axis. And here's a negative in front, so there's a reflection and a vertical translation on this function. So we'll look at those graphs really quickly so you can see what we're talking about. Here's the parent function, y equals 3 to the x. It has the behavior that we said, 2 to the x would have a while ago. It does have this y-intercept. It is strictly increasing over its whole domain, and it does have a horizontal asymptote that is the x-axis. So if we pick that entire function up and move it 4 units down in the plane, 1, 2, 3, 4, then that is just a vertical translation 4 units down in the plane, and we're used to that. We can handle those translations. Understand and remember, it will affect the range of this function. Once we pick a function up and move it up or down, or once we stretch it or compress it and do some things like that, it can affect the range of our function. So it will also affect the horizontal asymptote. The horizontal asymptote that was y equals 0 is now y equal -4. So let's look at the next example. This was the horizontal translation where the function was picked up and moved 1 unit to the left. didn't affect the horizontal asymptote, didn't affect the range, and of course doesn't affect the domain. But these are transformations, translations, exactly like we're used to. Everything that we know about transformations and translations or reflections on our other parent functions still hold true on these exponential and logarithmic functions. So no change for us. Here we just take the parent function y equals 3 to the x, put a negative in front of it. That means all of the outputs that were positive on f of x equals 3 to the x, the blue graph, are now negative. That means it's just a direct reflection over the x-axis. It affected the range, so now the range is from negative infinity to 0, but did not affect the horizontal asymptote. Still have the same horizontal asymptote, y equals 0, or the x-axis. In the last example here, we have that reflection over the x-axis, and it's been translated 2 units up in the plane. That's a vertical translation up in the plane. So here is negative 3 to the x. Sorry, here's negative 3 to the x, and then we lift that up 2 units in the plane. Now we have a horizontal asymptote that is y equals 2, and our range is negative infinity up to positive 2. So let's start talking about logarithmic functions and the graphs of logarithmic functions, what they might have in common and what they might look like. So here's a function, f of x equals log base b of x, some things that have to be true for us to have a logarithm. The base has to be positive, and the base cannot be 1. The domain of f is the set of all positive numbers. That's 0 to positive infinity. We cannot have any negative input values put into a logarithmic function. So the domain is 0 to positive infinity. The range is all real numbers, so it goes all the way up and down the y-axis. The graph will pass through the point 1, 0. So these graphs, logarithmic functions, will have x-intercepts. They will have zeros. They will have roots, where the exponential functions did not. So while all exponential functions pass through the point 0, 1, all logarithmic functions, as long as they have not been translated or reflected or moved, if they're parent functions of base b, positive, not 1, then they all contain the point 1, 0. They are continuous functions. They are strictly increasing for values of the base greater than 1. They are strictly decreasing if the base is between 0 and 1. So let's look at just in general what a logarithmic graph looks like. So it's strictly increasing, contains the point 1, 0, and it is a slowly growing function. It will come up here and it will go ahead and just level out. So here's everything that we talked about on the last page. So there's log base a of x. Here's what it looks like if the base is greater than 1, just like we saw on the last graph. Here's what it looks like if the base is in between 0 and 1. Strictly decreasing, still contains that 1, 0 point, that x-intercept, and that's basically what it looks like based on the value of the base. So let's look at transformations. So just like on the exponential functions, we can translate up or down, to the right, to the left. We can reflect them. And it turns out that all the transformations that we know on all of our other parent functions still work here. This basically is a vertical translation 2 units up in the plane. Here is a horizontal translation 1 unit to the right. Here is a reflection over the x-axis, and here is a reflection over the y-axis. So let's look quickly at those graphs. Maybe we can get all this done in one video. So you can see here is the parent function y equals log base 3 of x, and it has been translated 2 units up in the plane. So containing the point 1, 0, now it contains the point 1, 2. It still has the vertical asymptote, that is the y-axis, or the vertical line x equals 0. The domain is the same, still 0 to positive infinity, and the range is the same, negative infinity to positive infinity. This other translation was 1 unit to the right in the plane. So we take that x-intercept and move it 1 unit to the right. That changes the vertical asymptote over to the vertical line x equal 1, still increasing, and it affects the domain as well. Here is the reflection over the x-axis. No surprises there. Here is the reflection over the y-axis. No surprises there. So that's it. Come to class next time and we'll practice on graphing these types of functions.